Hello everyone, my name is Ibrahim Yildirim. I am pursuing PhD degree at Koç University in Istanbul under the supervision of Professor Ertuğrul Başar. Today I will present our paper named as Reconfigurable-Intelligentsurface-Aided Angular-Based Hybrid Beamforming Design in mmWave Massive MIMO Systems. Before start, let me briefly introduce the content of my presentation. First, I will give an introduction and motivation of our study. Afterwards, the system and the channel model will be described, and then the proposed RIS-Aided Angular-based hybrid beamforming technique will be presented by explaining the design steps of RF stage, baseband stage, and RIS phase shift matrix. After that, the numerical results will be presented for the achievable rate performance of the proposed scheme. Then the presentation will be concluded with the final remarks. In wireless systems, the propagation medium is known as a randomly behaving entity between the transmitter and the receiver. It has a degrading effect on the quality of the received signal because there are uncontrollable interactions of the transmitted radio waves with the surrounding objects. In this regard, reconfigurable intelligent surfaces can be considered a new way to manipulate these interactions to optimize certain system performance metric. Reconfigurable intelligent surfaces are man-made surfaces of electromagnetic materials, and they can be electronically controlled with the integrated electronics, and they have also unique wireless communication capabilities to optimize system performance. Precoding and combining are the essential signal processing technique of MIMO systems for uplink and downlink transmission to enable reliable transmission. In the conventional MIMO, the single-stage fully digital beamforming shown in here requires full channel state information and one power-hungry RF chain for each antenna. Due to its higher power consumption and hardware complexity, it's not applicable for the large antenna arrays of the massive MIMO systems. For reducing the hardware cost and complexity, hybrid precoding combining technique has been proposed as a promising solution which partitions the signal stage fully digital precoding into two stages. First one is RF stage and second one is baseband stage. Furthermore, the angular-based hybrid beamforming techniques can also decrease the size of the channel state information overhead by designing the RF stage with slow time varying channel characteristics such as channel covariance matrix, angle of departure, or angle of arrival. It should be noted that angular-based hybrid beamforming significantly reduces the number of RF chains and CSI overhead compared to fully digital beamforming, while providing the comparable achievable rate performance with fully digital beamforming. By keeping these important features of the RISs, we can combine RIS and the massive MIMO systems to achieve the targeted requirements for next-generation wireless communication systems. In this regard, we introduce an RIS-Aided Angular-based hybrid beamforming technique for mmWave massive MIMO systems requiring low CSI overhead and reduced hardware cost complexity by providing enhanced achievable rate performance. By considering the 3D geometry-based mmWave channel model, we propose a three-stage RIS-Aided hybrid beamforming design, including RF beamformers, baseband precoder and combiner, and RIS phase shift design. In system and channel model, we consider an RIS-assisted hybrid mmWave massive MIMO architecture. Here, there is a single RIS between the transmitter and the receiver, and the transmission is carried out via an RIS and non-RIS direct link between the transmitter and the receiver. In this model, the transmitter and the receiver side are equipped with uniform planar arrays. For the proposed scheme, we need to design 5 blocks to transmit or receive NS data streams as shown in here: BT, FD, FR, BR, and RIS phase shift matrix phi. In order to connect these baseband and RF stages, we need to place NT and NR RF chains at the transmitter and the receiver respectively. It should be noted that the number of RF chains are significantly smaller than the number of antennas as shown here. According to the system model, the precoded signal S at the transmitter is given in equation 1, with X being data symbol. At the receiver, the signal received from the RIS-assisted and direct link is obtained as in equation 2. And then, by using equation 1 and 2, the received signal after combining is written as in equation 3. The effective channel matrix seen from the baseband stage is also given here. In this work, our main aim is to efficiently design FD, BT, FR, BR, and Phi to maximize the achievable rate of the system as in equation 4. Here, the achievable rate should satisfy the transmit power constraint given in equation 4D and constant modulus constraint given in equation 4C. In our scheme, we follow the 3D geometry-based millimeter wave channel model. In millimeter wave transmission, contrary to the conventional rich scattering propagation environment, only a few spatial paths are experienced due to the scattering limited propagation conditions. Therefore, the millimeter wave channel will be sparse in the angular domain. Consider slow time varying azimuth and elevation angle of arrival and departure information is also given in this table. Here, the channel is composed of two parts. The phase time varying CSI is represented as GL, while the slow time varying CSI is represented as phi LR and phi LT based on angle of arrival and angle of departure. Then the channel matrix HL between the corresponding terminals with L being TR, TI and IR is given in equation 5. Here, HL is a sum of the contributions of CL scattering clusters, each of which contribute ZLC propagation paths to the corresponding channel matrix. Now I will introduce the proposed RIS-Aided angular-based hybrid beamforming design. The considered system model is shown in this figure. I will respectively provide the design of RF beamformers, baseband precoder combiner, and phase shift matrix of the RIS. Here we aim to design these 5 blocks to reduce CSI overhead and hardware cost by reducing the number of RF chains. From this point of view, first, the design procedures of RF beamformers is introduced based on slow time varying angular parameters. Afterwards, baseband precoder combiner is designed by the singular value decomposition and water filling algorithm using effective channel with reduced size. Finally, the phase shifts of the RIS, which enhances the system capacity, is obtained by applying the particle swarm optimization method. Considering the effective channel seen from the baseband stage given here, we aim to exploit all degrees of freedom provided by the channel and maximize the beamforming gain during the RF stage design. In order to optimize the receive or transmit beamforming gain and take advantage of all degrees of freedom enabled by the channel, the subspace spent by the slow time varying corresponding phase response matrices should be encompassed in the columns of FR or FD. After that, the columns of the RF precoder matrix are created using the transmit steering vector AT. The quantized angle pairs are defined as here to obtain empty orthogonal transmit steering vectors as the minimum number of angle pairs spanning the entire elevation and azimuth space. Then finally, the transmit RF beamformer FD covering the corresponding angle of departure support is developed here. Similarly, by following the same strategy, we can obtain the receive RF beamformers FR covering the corresponding angle of arrival support. After the design of the RF beamformers, now we need to focus on the baseband precoder combiner design using the low dimensional effective channel matrix. First, the optimal baseband precoder is obtained by using the right singular values of the channel matrix. The curly H matrix given in here, and we use the dominant singular values. And we also apply the well-known water filling power allocation approach. Then, considering the given RF beamformer, phase shift matrix and baseband precoder, we aim to design the baseband combiner that minimizes the mean squared error between the transmitted and processed received signals. In the last step, phase shifts of the RIS elements are adjusted by optimizing the achievable rate of the system by using the particle swarm optimization algorithm. Under given RF beamformers and baseband precoder combiner, the optimization problem for maximizing the achievable rate can be formulated as given in equation 20. In our PSO solution, the phase shifts of the RIS elements are modeled as the positions of the particles, and the objective function is considered as the fitness function of PSO. For each iteration, the velocity and the position of each particle are updated according to equation 21. Finally, after Q iterations, the RIS phase shift matrix is determined at the last iteration. For the numerical and simulation results, we provide comprehensive numerical results to investigate the performance of the proposed RIS-Aided angular-based hybrid beamforming system. Here, Table 2 presents the common parameters for all simulations considering the geometry-based mmWave channel model. The top view of the simulation setup, including the terminal distances, is illustrated in Figure 2. Here, the transmitter-receiver channel is assumed to be nearly blocked under non-line-of-sight conditions, while the RIS-assisted cascaded channel is assumed to have loss conditions. First numerical result, consider comparison of achievable rate performance of angular-based hybrid beamforming system with or without RIS for varying D1 and DTR distances. In this comparison, the RIS-assisted system with random and constant phase adjustment are also considered as a benchmark system. In Figure 3a, we compare the achievable rate performance for the angular-based hybrid beamforming system for varying transmitter array separation under fixed transmitter and receiver positions. In this scenario, it's clearly observed that RIS significantly improves the system performance when the direct link between the transmitter and the receiver is nearly blocked. Figure 3a also provides practical perspective for the effective positioning of the RIS. When D1 is equal to 20 meters, the achievable rate will be measured as 10.47 bit per second per hertz, while it will approximately reduce to 1/3, measuring as 3.24 bit per second per hertz for D1 is equal to 100 meters. In Figure 3b, the achievable rate performance of the angular-based hybrid beamforming system is illustrated, depending on the position of receiver, changing along the x-axis under the fixed transmitter and RIS positions. As seen from the figure, doubling the DTR will result in a performance loss of 22.85% in the PSO-based RIS system, 28.2% in the random phase RIS system, 57.03% in the constant phase RIS system, and 76.53% in the conventional angular-based hybrid beamforming system. While the constant phase adjustment contributes to the transmission by providing a reliable loss path, it will become saturated at increasing number of reflecting element values. Although the random phase adjustment also leads to a remarkable increase in the system performance, the effect of increasing MI is more evident for the PSO-based RIS-assisted hybrid beamforming system. As observed from this figure, increasing number of reflecting elements significantly enhance the effect of the RIS in transmission, both in the case of PSO-based and random phase adjustment. Finally, in this figure, the achievable rate comparison of the angular hybrid beamforming system is demonstrated in the presence of an RIS under varying number of RIS elements. For instance, the PSO-based scenario provides a 3 dB advantage over the random phase adjustments case for MI is equal to 10, while provides 4.5 dB increase for MI is equal to 100. Let us conclude the presentation with final remarks. In this work, we proposed an RIS-Aided angular-based hybrid precoding combining scheme for hybrid mmWave MIMO systems with low CSI overhead. In our proposed system, the RF stage has been developed by using only the angle of arrival and angle of departure parameters defined in the geometry-based millimeter wave channel model. And the baseband stage has been developed by using the reduced size effective channel. Then the RIS phase shift matrix have been designed by using particle swarm optimization algorithm to maximize the achievable rate performance of the massive MIMO systems. It is demonstrated with the extensive simulation results that the RISs significantly enhance the achievable rate performance of the angular-based hybrid beamforming millimeter-wave systems by alleviating the disruptive effects of the wireless propagation environment as well as reducing the CSI overhead size. This is the end of my presentation. Thanks for listening.